Learning IT is fun. Learning IT is interesting. And right now, IT is the most valuable skill to acquire. And in IT, one of the most important lessons to understand is binary. You may not understand everything, but at least you need to begin to understand it. The basics.
Hi, my name is Lamore Freed, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only two options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8's position, and so on. For example, the number 9 in binary is 1, 0, 0, 1. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only ones and zeros, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
So we started our lesson on the binary number system, and we've studied a lot about how binary is the only language of computers, how all programming languages came from binary and will be compiled back into binary for any software to work, how our electric signals are all binary, how our CPU only processes in binary, how data is stored as bits, and it stores them in chunks of 8 bits, and 8 bits is known as a byte, and how 1,000 bytes will give us 1 kilobyte, and how 1,000 kilobytes become a megabyte, 1,000 megabytes 1 gigabyte, 1,000 gigabytes will be 1 terabyte, 1,000 terabytes will be 1 petabyte, 1,000 petabytes will be 1 exabyte, 1,000 exabytes will be 1 zettabyte, and 1,000 zettabyte will be 1 yottabyte, and 1,000 yottabytes will be 1 brontobyte. We talked about other number systems in IT. We talked about the decimal number system, octal number system, hexadecimal number system. But we said all of these number systems are there to help data to be represented in an easy way for humans. But in the computer, it is all about binary. It is only binary the computer works with. So we learned how to convert from decimal to binary, from binary back to decimal, from text to binary, from binary to text. We looked at the ASCII table. We learned how you can use your keyboard to input in ASCII by pressing the Alt and entering the ASCII code, and you get the character you are looking for. We learned how to convert text into binary, and we learned that even your name can be written as binary code. This code here, it means hello. So when you learn how to convert binary to text and you see this, or you are given this code, you can decode it, and when you finish decoding this, you get hello. You can be given a whole message in binary code, a whole message. We learned that sometimes important or secret code can be written in, or secret messages can be written in binary codes, and only those who can decode will be able to decode and understand what it says. We took time to learn about images, how images are represented in binary and vice versa. We looked at how images work, and it was interesting to understand how computer technology does all of these. Today our job is to take a look at how sound is represented in binary. All right, so we are going to look at how computer stores sound. How sound is represented in binary. How sound is represented in binary. Right now that I'm speaking, I'm producing sound. Do you agree? Okay, so as I'm speaking right now, sound is being produced, and this particular sound can be captured by the computer and stored. So when we are talking about sound, first of all, we talk about how the sound is captured. We talk about how the sound is captured first. Then later, we'll talk about how the sound is played back, or how the sound is stored and played back. So it says that computer stores sound as binary. When sound is captured, usually by a microphone, it is an analog waveform or signal. But since computers are digital, not analog, the analog signal must be converted into a digital signal. This is what it means. As I'm speaking, I'm producing audio. Please, are you here? I'm producing sound. The sound in the physical world is in analog. The sound in the physical world is an analog signal, or is in analog. But inside computers, sound is digital. As I speak, my original sound is analog sound. My original sound is analog sound. When sound is stored on the computer, sound is stored as digital sound, because the computer uses digits to represent the sound. So the sound in the computer will become a digital sound. When I'm speaking, it is not from any digits or any digital system. When I'm speaking as a human being, I'm producing natural sound. So the sound I'm producing, what you need to understand about it is that it is analog sound. We are learning about how computers store sound. Right now, what I'm telling you is that the sound we produce is analog sound, and the sound the computer stores is digital sound. And so, for this computer to store our sound, first of all, there has to be a conversion from analog to digital. That is the first thing that needs to happen. It needs to happen because we are learning how computers store sound. And so, inside the computer, there is something that is called the analog to digital converter. There is something, a hardware called the ADC, the analog to digital converter. So when I produce sound, my microphone receives the sound as vibrations. When I'm speaking, my microphone receives the sound I'm producing as vibration, and it will send the vibration through its wires or its connections into the system. The computer doesn't know what I'm saying. The microphone doesn't know what I am saying. It is only recording vibrations. And these vibrations are recorded as waves. Or these vibrations is received by the microphone as waves. Let me open Cool Edit Pro, and I'm going to record something for you to see. Before I do the recording, I want to point out 7 things to you. Please, what do you see here? Which sample rate have I selected? 44,100. Because I want to stay at the basics, I'll not talk about the channels right now, but I'll talk about the resolution here. Which one am I using? 16-bit. These are the settings I'm instructing this recorder to record from the microphone. I'm giving these settings. Later I'll talk about these settings and you understand them. So when I click OK, a new recording window is open. And immediately I hit record, my sound starts getting recorded. Now whatever I say will be recorded. Can you see the waves? These are the sounds I'm making. And you realize that whenever I am not speaking, it is low. When I speak, it moves. When I speak louder, it becomes louder. Can you hear that? And so these waves are just recording what? Vibrations. Let me stop it. Sound is captured as waves. I can play this back right now. Sound starts getting recorded. Now, whatever I say will be recorded. Can you see the waves? These are the sounds I'm making. And you will realize that whenever I am not speaking, it is low. When I speak, it moves. When I speak louder, it becomes louder. Can you hear that? And so these waves are just recording what? Vibrations. Now these waves, are you here? I'm going to zoom in. Let me zoom into the waves. You see how the wave has become? When you zoom in, you realize that they are just lines. They are just lines. Because there are so many, when you zoom out, then you see them like this. So usually when we hear audio or when we see audio on a computer, this is how we see it. But when you go into it, you see that they are just waves like this. Are you here? Now we are talking about how my audio was captured by the computer. And how it was stored. For the sound to be captured, there is a term. I don't know who can see this. Sampling. Sampling is the process that does the storage. Okay, how can analog audio enter into the computer and be stored? Okay, now listen. What the computer does, after these vibrations go through the microphone, the ADC, which stands for what? The ADC does simple recordings. Simple recordings. Now, when I say recording, I'm just talking about writing. Listen to me. Or, let me put it this way. The ADC does simple measurements and records the measurement it gets. When these vibrations are coming through the cables or the microphone cable, records are taken. These records are simply the loudness of the wave. When I say loudness of the wave, let me use this graph to explain what I'm saying. Constantly, these waves are going through the ADC. So let's say that the line here, maybe you can't see, but there's a line here. That line is the line of the ADC. And these waves, let's assume they are traveling. They are moving. Now, at every point in time, a part of the wave will hit the ADC line. So, all that the ADC does is to write the height or the number it got. When this level hits the ADC, the number will be here. When this level gets here, it will be at this point. Now, how do you know the number? The number can be traced from here. Please, can you see the number here? So, right now, the ADC is at 6.2. When it gets here, it will be around 4.8. Over here, it's around 6. Over here, it's around 6.9. Here, it has dropped down to 2. So let me tell you how the computer stores sound. If this is the ADC line and these waves are passing through, what the computer will be storing will be 6.8, 4.8, 6, 6.9, 2, 9.5, 3, 4, 5, 8, 6, 2, 1. All the ADC does, listen to me, is to record numbers. Hello. The number is based on how high the wave is. Please, are you here? The number is based on how high the wave is. And how high the wave is also means that the volume at that point is high. Because the wave went high because the volume was louder. And when the volume is low, the number will be low. So watch this. The ADC, all it does is to write numbers. Do you see these numbers here? Okay. So it writes these numbers in decimal. It writes the numbers in decimal several times per second. It writes the number how many times? It writes it in milliseconds. Milliseconds. Have you heard of milliseconds? How many milliseconds will give you 1 second? Pardon? Okay. 1,000 milliseconds is 1 second. 1,000 milliseconds is what? Okay. Now let me make it more real, more realistic for you. When I was recording my audio, do you remember the sample rate I used? What did I use? 44,100. This is the instruction I gave to my recorder that record this audio or take samples 44,100 times in 1 second. Wait a minute. Maybe I've jumped too high. These numbers the ADC is writing down, it does that several times in a second. You see the line here is about time. You see the line here is about time. So let me just assume that this is 1 millisecond. So in 1 millisecond it will record. The next millisecond it will record. Let me move to the next table. Okay. So the next millisecond it will record. 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 It will record the numbers. These are the numbers it is recording, because these are the volumes of the waves that are coming through. I told you that the waves will be going through the ADC, right? And it will just record based on how high it is. Okay, so let's try something very simple. Let's try something simple. Now, the first number we picked here. Okay, let's start from the records here. The first number we picked here, what did we pick? We picked 8, right? Okay, so 8. If let's say we have a graph here, this are you following? This is a graph, just a graph. You all know graphs, right? In SS, you use graphs. So let's say this graph, we have 1 here. All right. So now, let's say you have a dot. What can we use for a dot? Let me use this and see. Okay, so this will do. All right, now at time 1 they say you should plot the number what? 8. So where will it be? 1, we will plot it here, right? Okay, so let's say we have our time here. We have our dot here. 2, they say you should plot the time at what? 3. So 3 should be somewhere here. Then 3 is what? 7. So 7 will be here. Somewhere here. Then 4, we have what? 6. 5, we have 9. 6, we have what? 7. 7, we have what? 2. 8, we have 9, we have 6. And 10, we have what? 6. Okay, fine. Now, do you see these numbers? When audio is being captured, it is numbers that are just being written down. Just numbers that are written down. The first number here, we said it is 8, right? When this 8 is written down, do you know that 8 can be converted into binary? Can 8 be converted to binary? Let's convert 8 into binary. To convert 8 into binary, you ask yourself, how many times are 2 go into 8? 4 times. Remember what? Then, how many times does 2 go into 4? Remember? How many times does 2 go into 2? Remember? How many times does 2 go into 1? 0. Remember 1. If you want to get the binary code, you read from the bottom to the top. So the binary code is 1000. This is a binary code. In the book, what did they record here? The same thing. So they converted it. Alright. So watch this. This is what I want you to get. When the number is recorded as 8, the 8 is converted to binary, and that is very easy to do. Now watch this. Watch this. When we finish, our job is to join the lines. Let me join this line to this. Please, are you following? Yes. I'm joining the lines. Okay. When I finish joining these lines, I go like, this thing is beginning to look like a sound wave, but it doesn't look very correct to me. Watch this. Look at the original sound wave we all recorded. Were you here when we recorded this? Please, were you here? Yes. Okay, this is what we recorded. What is the difference between this original sound wave and this one we have here? What can you see? They are samples, but what do you see? Just tell me the difference you see. What you see? The lines are too straight, right? Excellent. That's what I wanted to hear. Now, when you look into the book, this is the sound we are using. Or this is the original sound. When we finished, this is what we got. You see what they got here is the same as what we got. Can you see what they got in the green line? Okay. So the question here is that how can we make this wave look like the original wave? How can we make it look like the original wave? And I'm going to ask you to think about it for a second and tell me. You see, this one is very smooth. Okay, if we play this, if we give this to a speaker will play it, but it will not be like the original. It will be a very low quality audio. Very low quality. For this audio to come out well, it needs to, the way we get here finally, needs to look like the original. So my question is, who can tell me what we can do? Tell me what we can do to try and make our wave look like the original wave. What can we do? What can we do? Okay, now watch this. One of the things we can do, or one of the things we didn't do here, is that the distance between the capturing or the recording of the numbers is wide. Please, are you here? The distance between when the numbers were recorded, the gaps we use are too wide. Now, if you record one sample, or you write down the sample in 1 second, your sound will just be noise in the speaker or in the speaker. Nobody will hear anything. If you want to hear the original audio, you need to record several times per second. You need to record how many times per second? If you just take 1 per second, you will get a wave like this. Please, are you with me? I said this is millisecond. Let me call it second for the sake of the explanation. If you just take 1 recording per second, your wave will look like this and will not look like the original. So, to get it closer to the original, you need to record several times per second. Now, for me to tell you the real interval the computer uses to record or to write down the numbers, that interval is called the sample rate or sample frequency. When I was recording my audio, what was my sample rate? 44,100. So, to get the original sound, you need to use a sample rate of 44,100. If you can record the points 44,100 times in 1 second, when you finish and you plot, your graph will look just like the original. Because they are so close to each other that they form the smooth curve. In 1 second, you record 44,000. Okay, now let's read what is here and see if it will make a little bit of sense. Now watch this. Computers store sound as binary. When sound is captured, usually by a microphone, it is an analog waveform or signal. But since computers are digital and not analog, the analog signal must be converted into a digital signal. To do this, an analog to digital converter, ADC, needs to do what is known as what? Sampling. Sampling means a specific interval of sound is read and converted to a value. These samples are taken at regular intervals or specified sample rate. We are saying that they are taken as regular intervals and converted to a number, an integer. The number that is recorded is then converted to binary. If the number recorded is 8, that 8 can easily be converted to binary. For example, a sound wave like the one below can be sampled at each time sample point. So when you check these points here, what it does is that it is just recording the height of the wave. It is just recording the height of the wave. It's just recording, writing down numbers. Okay. So those numbers can be written down as just decimal numbers and then converted back into binary. The binary codes taken at each time sample are then joined together and stored in the computer. Let me copy the binary code here and paste it somewhere here. Watch this. When I paste this binary code and I tell you this is sound or this is music, if you don't know, you will not believe it. But this is audio. This code you are seeing is audio. When we finish, we will look at how the computer will convert a binary code like this or a binary code like this to sound for us. When we finish, we will look at how a code like this can be played as music. Now we have learned that the sound can be stored in this code, and it's simply writing down numbers of the height of the waves, because it is just waves passing through your ADC, and it is just writing based on the volume or the height. Okay, watch this. Watch this. If the time samples are then plotted back onto the same graph, it can be seen that the sound wave now looks different. This is because sampling does not take into account what the wave is doing in between each sample. So when we record, it doesn't take into account of all of this. The first thing we are trying to understand is how wave can become binary. And we have learnt that, and what we said is that the wave passes through an ADC, and the ADC records the point based on how high or how low it is. The numbers that it writes down can then be converted to binary. Does that make sense to you? The numbers that it writes down can easily be converted into binary. And so we can have a binary code which is sound. Second question: how can this binary code be played back as sound? That's the second question. If we have a binary code and we say this is audio, how can binary code become audio? The first information the computer needs to be given is this: your samples that are taken, how many bits do you use to take each sample? Because if the computer doesn't know how many bits it uses, it will fetch the code in the wrong amount. Over here, the samples that were recorded, how many bits were used to record each sample? Pardon? 4 bits. 4 bits. Please, do you remember? I mean, can you see? It's 4 bits, right? So each sample was recorded in 4 bits. This is also one of the reasons why our wave is not very quality. When when I was recording my audio, the resolution, how many bits did you see? 16 bits. And so when computer sees binary code and we say it is sound, the first question it asks is that how many bits do you use to create your points or your samples? If you have 16 bits, then you can get original audio that a human ear can interpret correct. Because we are learning in bits, or we are learning small, that is why we are using 4 bits here. But the original audio was in 16 bits. Okay. You can also record an audio in 8 bits. Please, can you see? You can also record an audio in 8 bits. Okay. Let's assume this audio is in 8 bits. So we will take our first 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, space. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, if I give you this code, can you convert it into a number for me? Hello? I'm asking a question. If I give you this code right now, what I've highlighted, can you convert it to a number for me? You can convert it into a number. Please convert this code into a number for me right now. I'm talking about a decimal number. All right, so let's go ahead and do it. Do you remember this table? This is a table we use to convert binary to decimal, right? So we'll feed the code here. Did you record the code? Pardon? Is that the code? The code I gave you. Is that not it? Is that not it? So this code, what number will it give you? What number will it give you? 128 plus what? Plus equal to 13. So you have a number, right? This number, all you have to do is to go to the sound graph and mark it. And we are taking 44,100 times in 1 second. So in just 1 second, we will take in pieces 44,000 times. So when you plot those numbers, 44,000 times in a second, by the time you join them, it will look so smooth because they are so close together. So the computer is able to play this as audio because it picks the number of bits and converts to numbers and plots the numbers on the graph. When the numbers are plotted, it becomes just like a wave like this. So binary can become a wave like this. Hello? Binary can become a wave like this. Does it make sense to you now? Binary can become a wave like this. I said, does it make sense to you now? Now, this wave, speakers are designed to play these waves. When these waves are played, listen. My sound starts getting recorded. Now, whatever I say will be recorded. Can you see the waves? These are the sounds I'm making. And you realize that whenever I am not speaking, it is low. When I speak, it moves. When I speak louder, it becomes louder. Can you hear that? Did you hear that? So, what you are seeing is just the speaker playing the waves back. This lesson, you can take it into details and go deep. If you want to be a sound engineer, you can go into details and learn a whole lot about it. But we just want to understand that computer stores sound as binary. And this binary can be played back as sound. And that is what we have demonstrated. The last part of the note says that when you plot your chart and it doesn't look the same, this means that the sound loses quality as the data has been lost in between the time samples. The way to increase the quality and store the sound at a quality closer to the original is to have more time samples that are closer together. That's why we talked about the sample rate. This way, more details about the sound can be collected. So when it is converted back to analog and played back, it does not lose much quality. So the only way you lose quality is because of the intervals. If your intervals are too wide, you will lose a lot of quality. But if they are so close, and I told you that original sound is in how many intervals per second? 44,100. There are some systems that take even more than 44 and gives us extremely high quality. Some record 48. Now, the frequency at which samples are taken is known as a sample rate. We talk about sample rate, and it is measured in hertz. 1 hertz is 1 sample per second. Most CD quality audio are 44,100 hertz or 48,000 hertz, not kilohertz, hertz. So some take 48,000 hertz. And there are some new sound systems that take audio and playback audio at 92,000 hertz. Those are extremely high quality sounds. Have you ever been in a studio before? If you've ever been in a studio, either a recording studio or an FM studio, you will realize that inside the studio, sound quality is so rich. It's so high. When you record music in a studio, the music in the studio is so rich. When it is coming out to the public, it uses the quality of their radios and their sound systems. And so if their sound systems are not very quality, they will hear it in poor quality. But the original sound is very high quality. And so we have a lot of audio formats. Have you heard of MP3 format? MP3 format is a format for distributing audio, and the quality of MP3 is a little low. Most original sounds are stored in a format called WAV, WAV. If you find any audio in WAV, you will see that the quality is higher, but then the file size is also large. An audio that is 100 meg in WAV will be like just 3 meg in MP3. Because MP3 will reduce the file size, it can easily be shared for people to hear on their WhatsApp and other platforms. But then the quality of the MP3 is low. When you play it, you may not detect the quality loss, but the quality has still been reduced because the sample rate of the original is different from the sample rate of the MP3. All right. So today we have looked at how computer stores sound as binary and how it plays back binary as sound. This is what it is, and this brings us to the end of our lesson on binary.